Okay, good morning. So, let us get started from where we left last time. So, if you remember last time we were looking at the earliest deadline first scheduler, the EDF scheduler. We had said that it is a good one, it is a very good scheduling algorithm, rarely used and so on. So, let us just catch up on that and proceed from there on. So, we had said that it is the optimal algorithm. EDF is the optimal algorithm, and if set of tasks cannot be scheduled using EDF, then we can have no other algorithm that can successfully schedule the set of tasks. It also can schedule both periodic and aperiodic tasks. These are positive points, and we had said that what are the scheduling points for EDF? What do you think? What are the scheduling points for EDF? Yes, anybody like to answer?
Highest priority can schedule it first.
No, what is the scheduling point? A scheduling point, can anybody say what is a scheduling point for any real time task scheduler?
The start of frame.
No, the scheduling point is the point on the timeline at which the scheduler wakes up and decides which task to run next. In a time driven scheduler, we had said that at periodic clock intervals, the scheduler wakes up and decides what to do next, right. Possibly it consults a table, tries to see which tasks need to run now. But what about EDF? What are the scheduling points? Anybody like to answer? Is it a time driven scheduler or an event driven scheduler? What about EDF? What do you think? Is it a clock driven scheduler or is it an event driven scheduler? No. We had said that the clock driven schedulers are the simplest ones, and we had discussed two clock driven schedulers. One was the table driven scheduler and the other was the cyclic scheduler, right. And we had said that those are simple, used in very simple applications. The main difficulty with that was when the number of events increases, it becomes very difficult to construct a schedule, and also for aperiodic and sporadic tasks, the clock driven scheduler can't handle them because they occur anytime, not according to a clock signal, isn't it? Then we had discussed about the event driven scheduling, said that any application that is slightly complicated, many events are there and some of the events are aperiodic or sporadic, then we will have to go for a event driven scheduler. And then we said that lot of results are available, but two algorithms which actually summarize all the results in this area. If we know those two algorithms, we know all about event driven scheduling on a uniprocessor, and those we said the EDF or the earliest deadline first algorithm and the rate monotonic algorithm. And how does the EDF work? Can somebody answer this question? How does the EDF scheduler work?
Whenever the task arrives,
yes,
then it looks for its deadline.
Yes.
And then it sees all the deadlines and
okay. It finds the task which has the shortest deadline and selects that. And when does that do it? At what points? But what are the scheduling points? Correct, it does that at scheduling points, but how are those scheduling points known? Or on timeline, at what points on the timeline will the scheduler wake up?
Whenever the event a new task arrives,
yes,
that time it has to see whether
of course,
is
yes. So a task arrival and also task completion, right. These are two events that define the scheduling points, right, the task arrival and the task completion. So at any scheduling point, the scheduler dispatches the task having the shortest deadline among all ready tasks. Very simple algorithm. Checks the tasks, the one that has the shortest deadline, it dispatches it. And of course, if there is any task that is already running, then this will preempt it and let the task which has the shortest deadline run. Very simple algorithm. Now, we had tried to define a check on given a set of tasks. How do you know whether it will be schedulable or not? It said that the check is simple, check whether the utilization due to all the tasks is less than 1. And this is true for any scheduler. Why EDF? Even the traditional scheduler, as long as the utilization due to a task is more than 1, it cannot meaningfully run, isn't it? So, this restriction is actually obvious. For any scheduler, it holds that if the computation time requirement for the time in which it arises, the sum of all that is more than 1, it cannot be scheduled. So, it is very simple condition here, and this is both the necessary condition and a sufficient condition for schedulability. So, we had looked at some examples last time, and we had said that, see, given any 3 tasks or any set of tasks, how do you decide whether it will run using a EDF scheduler successfully or not? The only thing that you will have to do is find out the utilization, that is EI by PI for each of these tasks, and see here the period and deadline is the same. That is true for almost every real time task that you will encounter. Rare cases, the deadline will be different from the period. So, find the utilization 1 by 4 plus 1 by 5 plus 5 by 20, sum it up, check whether it is less than 1 or not. As long as it is less than 1, it will run successfully using EDF. And then we were discussing that why do we call it as a dynamic priority algorithm, because it does not have a concept of priority at all. It just finds the one that is shortest deadline and just runs it. But then we said that, see, if you look at the working of the algorithm, it just a task that is waiting for some time, slowly the chances of it getting selected for running increases, isn't it? So, we can think of a virtual priority that is associated with tasks and which keeps on increasing at the task waits. Right. So, there is no real priority value associated with tasks.
The priority keeps changing dynamically.
Yes, that is a virtual value, that is for our own understanding, but actually it works without using a concept of a priority. It just looks at the deadlines and just schedules, right. So, that we had discussed. Now, let us proceed further. So, we had said that we can't really determine the priority value of a task at any point. We can't give a number 20 or 30, and we can't really say that from 20 it has become 19 or 21, etc. No, it is only a virtual priority value which we can imagine a value associated with a task which keeps on increasing with time until the task is taken for scheduling. If we look at the EDF critically, if we try to evaluate it, we will see that it is a very simple algorithm. It just looks at the deadlines and selects the shortest one, but it is optimal. If it cannot do something, it cannot successfully run a set of tasks, no other algorithm can run, but is rarely used. When we look at the commercial operating systems, you will see that almost none of them directly supports EDF scheduling. There must be lot of disadvantages.
So, does it support indirectly?
Indirectly, you can write a scheduler, yes. See, you have you can write a scheduler, a custom scheduler for a operating system. Most of the commercial operating system will see that they give you facility to write your own scheduler and to run it, and even select between 2-3 scheduler as the system runs.
So, in practice, whether it is being used?
In very rare cases, EDF is used, very rare cases, because of its problems. If we have an application for which these problems are nothing, then EDF is a good algorithm. Let us see the problems.
So having one question.
Yes.
So now you're saying that if task having 5 milliseconds,
Yes.
okay, this is running, the another task is coming,
Yes.
it having deadline only 3 milliseconds.
Yes.
Process.
Yes.
Okay, it's pre-emit that
5 millisecond task.
it's
Yes.
taking the 3 milliseconds.
Right.
Another task is coming at 2 milliseconds.
Yes.
The period.
Yes.
So it will again pre-emit this 3 milliseconds. And it will take
Exactly. Exactly. See, the question that he asked now is that what if one task is running that has, let us say, 10 millisecond as the deadline, right? That task was running because that was the shortest deadline that time, and as it was running, we had another task which just arrived which had 5 millisecond deadline. So that task will be taken up, this task will be preempted, and then as the 5 millisecond deadline task was running, another task came, very short task, which had a 3 millisecond deadline. So that task will be taken up, and after that completes, the 5 millisecond task will be taken up.
Then it may miss the deadline.
See, as long as the utilization is less than 1, it will ensure that all the deadlines are met. You can just try out in your notebook, take task combinations, see if there is a situation where the deadline is missed and the utilization is less than 1. Just let us construct such an example. Of course, theoretically it has been proved, very easy to prove actually, that if the utilization is less than 1, then the deadline will be guaranteed to meet. That has been, that we can prove easily. I did not take up the proof, but you can also try proving that, right? Does that answer your question?
Yes, sir.
Yes.
Now the 10 millisecond thing,
Yes.
okay, 6 milliseconds is over.
Yes.
Another 4 milliseconds is left.
Yes.
That time, if 5 milliseconds is occurring,
Yes.
the period process having 5
Yes.
milliseconds, it's occurred. Now what it will do, sir? Whether it will take the 10 milliseconds to proceed or 5 milliseconds.
Okay. So the question is that a task which had 10 millisecond as deadline has computed up to, let us say, it started sometime, and at 6 millisecond it had not completed. So it has only 4 millisecond remaining, and there is another task which has come up which has 5 millisecond deadline. So the nearest deadline is the one which had 10 millisecond originally, isn't it?
So on the
So,
timeline we have to see.
yeah, we have to see what is the deadline remaining for it. So the one which had 10 millisecond at some point of time, right? Now at another point of time it has only 4 millisecond left, and a task which has come which has another 5 millisecond deadline, obviously the one which has 4 millisecond will run, isn't it? Yes. Is that okay? Okay. So let us proceed. We said that there must be severe disadvantages of this algorithm, otherwise people would love to use this. It is a good algorithm, simple, efficient. Okay, let me not use the word efficient, simple and optimal algorithm. So let us see the main disadvantages of EDF. One of the severe disadvantages is that it has poor transient overload handling. We will elaborate this as we discuss, and then it is inefficient, runtime inefficiency. And the most important or the most severe shortcoming is that it cannot support resource sharing among tasks. Actually, even if you try to support tasks that share resources, see that the performance becomes really unusable and tasks miss their deadline.
But it must be possible, sir, because the tasks are, there is only one task executing at a time. So in that case, it must be able to share the resource.
Okay, so let us hear others answer. What do you mean by resource, and why resource sharing is necessary among tasks? What is a resource?
Some task requires that previous output,
Yes.
previous task output.
Yes. Yeah, that is one way. Like let us say they are working on, let us say, some data items, and one task is modifying that data item, and another task also needs to use that data item. So unless the first task completes, the other one cannot use it, isn't it? And if the other one uses, the data will become inconsistent, right? So these are the critical resources actually. So one common example is certain data structures.
Mainly the data structure.
Data structures, memory locations, files, devices, etc. can be critical resources, right?
But devices, if you say that must be shareable.
See, until one task completes its use of that device, the other task cannot use it. So, that becomes a critical resource. Of course, if you look at the traditional operating system, printer, even though it is a device, is not a critical resource because of spooling, right. That is a first level course, let us not spend time on that. Due to spooling, printer is not a critical resource because a task just outputs whatever it wants to output and gets stored in a file. And meanwhile, another task also can output to the printer which just gets queued. So, but there can be devices which are critical resources. Until a device finishes reusing that resource, another device can use it, right. Okay, so let us elaborate these three issues. The first disadvantage we had said that poor transient overload handling. But what exactly is a transient overload and why does it occur? Anybody like to answer this question?
Because of infrequent or frequent arrival of tasks, there could be switching between the.
No, what is a transient overload and
there will be overload on the system.
Overload on which system?
On the scheduling algorithm.
Not on the algorithm. The overload means the processor demand for tasks suddenly increases, right. So, suddenly many tasks have risen, all have their completion time requirement and the CPU is overloaded. It's even if it is working 100%, right, or it has to work really 100% for them to meet their deadlines. Earlier many times the CPU was idle, now the CPU is getting overloaded, right. We are talking of the CPU overload, right. Now, why should a overload occur? Can somebody answer this question? Why should transient overload occur? Transient means the overload occurs for a very short time. Let us say for 1 second, it was working for 1 day, nothing, it was working fine, but for 1 second, suddenly many tasks arrived and the system was overloaded. So, why should this transient overload occur? Under what situations?
Maybe environmental conditions.
Environmental conditions. No, not clear. I mean, what environment? Can you just give some example?
Like suppose if you take avionics system.
Yes.
Many systems are failing or giving unwanted output, and accordingly they are behaving undesired.
Okay.
So they.
Okay.
Right.
So there are one situation is that some events, like he was saying, that some events they cause many tasks to arise at the same time. The simplest example may be a fire condition was detected in the building and then we have to sound the alarms, we have to start the water sprinkler, we have to inform the security, many tasks will arise at the same time, right. So, one reason for a transient overload is that some event has occurred which is triggering many tasks at the same time, but there may be other reason also. So, let us see that. There are two main reasons why transient overloads occur. One is too many tasks arise on some event, like we were saying. The other is that a task which was supposed to complete within some time is taking more time, more than the expected time it is taking. Maybe it has gone into a loop or it is gone into some inefficient algorithm, is taking too much of time, and the other tasks, the CPU will get overloaded, right. The other tasks are waiting to run. So, these are two situations where transient overload might occur, and when a transient overload occurs using the EDF algorithm, it becomes extremely difficult to predict which algorithm will which task will miss its deadline. So, even the most critical task can miss its deadline, whereas something which is non-critical like a logging task which logs the result might actually be running successfully, whereas another task which is supposed to be a very crucial task might miss its deadline, right. That will result in a system failure. So, using EDF, a main problem, one of the main problem is that when there is a overload situation, we can't really predict which task will miss its deadline, because criticality etc. is not taken into consideration. It is only based on the deadline. Okay. So, that is one disadvantage. Now, let us see the other disadvantages. EDF is not very efficient. In a typical implementation of EDF, the tasks have to be maintained sorted according to their deadline, so that we can pick the shortest deadline first. If you do not keep them sorted, it will become still more inefficient, is not it? So, here you maintain them sorted, and one data structure which is can implement most efficiently a priority queue. Okay, let me just ask this question: which is the most efficient data structure which can efficiently implement a priority queue? Yeah, heap is the, if you revise your data structure course, you will see that heap is the one where a priority queue can be most efficiently maintained. And using a priority queue, the complexity of maintaining the set of tasks in the order of their deadline, I mean each time you are able to select the shortest deadline, will be log n base 2. And that you need to do each time, is not it? Each time a task arrives, and if the number of tasks waiting there is large, it becomes very inefficient. Now, the third disadvantage, as we are saying that this is the most severe disadvantage, is poor resource handling. So, if in a practical situation, the tasks need to share many resources, for example, data structures, and in operating system literature we will see these are called as critical sections. Later we will discuss in more detail about that, how resource sharing is supported among real time tasks. And if you try to support resource sharing among tasks, you will see that it becomes extremely inefficient. Very likely tasks will miss their deadlines, and we will discuss this in more detail later on. But possibly this is the most severe disadvantage, because in real life situation tasks will need to share resources, and using EDF it becomes very, very difficult. Now, what if the deadline and the period are different? See, earlier we had said that the schedulability condition is EI by PI, and assuming that PI was equal to DI. But we can have some examples of tasks where the deadline is different from the period, possibly smaller than the period or larger than the period. So, we need to generalize the schedulability criterion. So, this is the criterion actually. If DI is the deadline and PI is the period for the task TI, and EI is the execution time requirement, then for every task we will have to find out EI by minimum of PI by DI. If DI is 10 and PI is 50, so deadline is 10 millisecond only after the task has arisen, and the period is 50 millisecond. We should consider 10, because by 10 it should complete. Or in other words, we are converting that task which had a 50 millisecond period to a 10 millisecond period, right? EI by minimum of PI DI, it is as if that task had a 10 millisecond period. Yes, please.
In the disadvantages we mentioned about the EDF,
yes,
we did not mention anything about the schedulability criteria, that the task may not be schedulable if we are using the EDF. If the tasks are not meeting the EI by PI criteria.
No, that see the question is that whether the constraint that we are saying EI by PI, the summation of that should be should be equal to less than 1 for a task set to be schedulable. It is not at all a disadvantage for this algorithm. Actually, None of the algorithm can ever run a task set whose ei by pi is greater than 1, impossible.
Condition is applicable to all the.
It is for all scheduler, it is true, because a processor cannot run, we are assuming at the same time 2 tasks. It cannot have no utilization more than 1, we are considering uniprocessors running only single thread, right, single task at any time. So, let us proceed. So, we are saying that in some situations pi might be different from di, and then we need to consider the minimum of that. But just see here, one problem is that it is pessimistic, in the sense that if the task set which is having a deadline of 10 millisecond, but the period is let us say 50 millisecond, it is not really occurring every 10 millisecond, it is occurring at after 50 millisecond, is not it? But here implicitly we are assuming that it is occurring every 10 millisecond, converted basically ei by minimum pi by di. So, we made it ei by di, right. So, you can say that it is slightly conservative. It may run if even if this criterion is satisfied. So, this is a sufficient condition, but not a necessary condition. Can you, as a bonus mark, construct an example where this condition is not satisfied, but the task set runs successfully using the EDF? Please try that. So, di is less than pi, okay, di is less than pi, and this condition is not satisfied, but still the task set will successfully run. Please construct such an example. Now, the other situation is if pi is less than di, it becomes a sufficient condition, not a necessary condition. Similar thing again. So, please check the characteristic of this algorithm, whether this is a sufficient or a necessary condition. Please prove it with, I mean, constructing examples, right. Please try that. Look at the 2 situations, pi is less than di and di is less than pi. Please check these 2 conditions. For both these conditions, please see if you are able to construct examples which will.
What is the second condition?
No, there are 2 conditions. One is the deadline is occurring after the period. So, that is this one we have written here, deadline occurring after the period, or pi is less than di. The other one is di is less than pi. So, for both these conditions, please check whether it is a sufficient condition, but not a necessary condition, or it is both sufficient and necessary. Please check that. So, that is a bonus problem. Please work it out and submit it to me. How does one implement EDF? I was saying that you would be able to write schedulers and you can plug it into the operating system. It will use your own custom scheduler. But if you want to use EDF, what will you have to do? We had said that a simple FIFO queue would become very inefficient, where you insert it at the end of the queue, and so the inserting is trivial, isn't it? one time, just insert at the end of the queue. But each time you want to select a task, you will have to scan the entire queue or ON each time, all n tasks you would have to see, and you would not want to do that, like to use a sorted queue. But we had said that sorted queue can be implemented using a priority queue, etc. But can a more efficient implementation of EDF be made? Yes. The implementations of EDF, those who would like to use it, possibly can be like this, that you consider several queues, each one holds the tasks within certain deadline. For example, 10 to 20 millisecond one queue, let us say 21 to 30 millisecond another deadline, and so on. So, a queue is maintained for each distinct deadline, and when a task is arrives, it is put into the appropriate queue, inserted in the appropriate queue. So, these are the deadline levels. So, each time, and within each queue, of course, you will have to keep them sorted, right, and each time also you would have to pick the task, you just pick from the top queue. Here this is the shortest deadline, right, otherwise if this queue is empty, check here and so on. So, please do an analysis of this efficient EDF implementation, again another bonus mark. Please check out what is the complexity of this compared to a priority queue, simple priority queue, where you have a set of distinct deadline levels. The time and space complexity, please compare and check whether it is an efficient implementation and what kind of benefit shall we get by doing this kind of a implementation of EDF. So, that is a bonus mark. As somebody submits a good answer, I will discuss that here. Please try to submit. There is no time limit for when you can submit, but please try to submit as soon as you can think of it. Search all the literature that is available, think about it, consult anybody, whatever, does not matter. But only thing is that the one who has submitted and appears to have done the work, he will be awarded the mark. Okay. For the same answer, 2 will not get the mark, because this is not a assignment, it is a bonus problem. You need not submit it, but those who submit, I will just check what is the thinking they have done, what kind of effort they have put, searching the literature, etc., right, based on that will award marks. Now, the EDF that we discussed, there are several variations of that. As I was saying that this is the basic algorithm and a large number of them were proposed. Possibly one important variation is the MLF, or the minimum laxity first. See, in the earliest deadline first, at any instant of time, we were just checking which task has the shortest deadline. But in the minimum laxity first algorithm, we check what is the amount of work remaining for a task and how much is the deadline. So, if a task deadline is, let us say, 10 millisecond, right, and another task, and the 10 millisecond task has completed 50% of its work. So, let us say another only 2 millisecond is remaining, and it has 10 millisecond as the deadline, 2 milliseconds work remaining and 10 millisecond is the deadline, and another task which has 12 millisecond as deadline, but 6 millisecond of work remaining. So, that algorithm will be taken up, even though its deadline is later, but it has more work remaining. So, that one will be taken up. This is the minimum laxity first, right. The laxity as written here is the deadline minus the time required to complete the task execution. So, how much it has completed so far and how much more computation it needs. So, the deadline was 10, but it had already completed 2 out of the total requirement of 4. So, only 2 was required for this. So, 8 is the laxity for that. For the other task that we discussed, the second task, 12 was the relative deadline from that point, but it had not completed any work and it required 6 millisecond to complete. So, its laxity is 6, whereas the other one having deadline 10, the laxity was 8. So, the idea behind this algorithm, a variation of EDF, is that the task that is most likely to fail first is assigned highest priority. So, it is the task, if it since it has the least time, lax time to complete, it is the one under overload or whatever situation, that is the one which is likely to miss its deadline. For example, another higher priority task arrives, right. But of course, it is obvious that when the execution time and deadline is the same, all the tasks have equal execution times at deadline, then EDF is the same as minimum laxity first problem. So, the bonus problem here is that analyze the performance of minimum laxity first and EDF. So, 3 bonus problems are already announced today. So, these are good opportunities to get extra mark from teacher's assessment. So, analyze the performance of MLF with respect to EDF, check which one is more efficient, which one can schedule a set of task not schedulable by others. Okay, these 2 points, please compare them. So, now let us look at the rate monotonic scheduler. So, this was actually the focus of this hour's lecture, but while reviewing the EDF that we had discussed last time, you had lot of questions and we spent quite a bit of time there. Now, let us look at the rate monotonic algorithm. This is the one which is most widely used in all real time applications. So, here the algorithm is again simple. The programmer needs to assign priority here. See, earlier we had no notion of a priority. In EDF, there was no notion of a priority. The scheduler just looked at the deadlines. The only thing that we possibly needed to do for the scheduler was to declare the deadlines and the execution times, right. But here the programmer has to assign the priority to tasks. So, how does the programmer assign priority to tasks? It will check what is the frequency with which the task occurs, or in other words, what is the period. If a task has, let us say, period of 100 millisecond and another one has period of 10 millisecond, then the frequency of the 10 millisecond task is high, isn't it? By the time one with 100 millisecond occurs, this 10 millisecond task could have occurred 10 times, right. So, the 10 millisecond task will be given higher priority by the programmer if he wants to run it under rate monotonic algorithm. So, this is the plot actually.
To be done
Yeah, before the program runs actually, the programmer should have decided by looking at the task characteristics, what is the priority of which task, done statically before the program starts, done by the designer. Is that okay? Now, let us proceed. So, the priority value increases monotonically with the frequency or the rate. Rate is the frequency.
We also decided
beforehand. Yes, of course.
And priority is also decided before.
Yes.
Why is there a relation between the two? Means we have 2 variables and they are dependent on each other, then we should decide.
No. The priority is dependent on the rate. Rate is the basic characteristic of a task. Priority is not the characteristic of a task. The priority is a dependent variable on the rate.
So, the programmer should decide either the priority or the rate?
No, programmer cannot decide the rate. See, for example, let us say a temperature needs to be sampled every 100 millisecond for a, let us say, a air conditioner to work, right. So, that rate is fixed by the task characteristic. What the programmer can do is look at 100 millisecond and check if another task needs 200 millisecond, every 200 millisecond it needs to be sampled. So, then the 100 millisecond task will get a higher priority, or the programmer has to assign that as a higher priority. So, the rate is the independent variable here, rate or the frequency, and the priority depends on the rate, and this is fixed by the programmer. Monotonically, the priority should increase with the rate. So, that is the algorithm. The priority should monotonically increase with the rate. Is that okay? Simple algorithm, and it is also the optimal uniprocessor static priority algorithm. See, in the EDF we said that it was a dynamic priority algorithm because the same task at different points of time it will get different priorities, or it after it waits for some time it just gets precedence over other tasks and so on. But here once you fix the priority, As long as there is a higher priority task, even if it is waiting for a long time, it will not run. Okay, but it is an optimal static priority algorithm. What it really means is that as long as you assign priorities statically, if RMA cannot schedule, then no other static priority algorithm can schedule. But of course, a set of tasks which RMA cannot schedule, EDF can possibly schedule, because EDF is optimal algorithm including all dynamic and static priority algorithms. But RMA is the static priority algorithm, optimal static priority algorithm. Something not schedulable by RMA can be schedulable under EDF. Okay. So, how do you check the schedulability? One is of course the utilization bound, because a processor cannot run two tasks at the same time, running only on a uniprocessor. So, this is the same thing we had for EDF. The same restriction holds here, but we will have additional restrictions. So, the necessary condition is that the utilization due to tasks is less than 1. But even if this is satisfied, a task may not run successfully under RMA. It is just a necessary condition, it is not a sufficient condition. So, the sufficient condition was given by Liu and Leland 1971. As I was saying that most of the research in these areas were done in 1970s, 60s. So, this was one of the very prominent result. I think any real time scheduler or any real time book will have a discussion on the Liu-Leland algorithm, very basic algorithm. We have just calling it as the utilization bound 2. If Ui is the utilization due to the task, that is sigma Ei by Pi, should be less than n, n is the number of tasks, and into 2 to the power 1 by n minus 1. So, if this condition is satisfied, then the task set will definitely be schedulable. So, this is a sufficient condition. The Liu-Leland condition is a sufficient condition. You can take a set of tasks and then check whether this is satisfied, n into 2 to the power 1 by n minus 1, as long as it is less than, greater than the utilization of the set of tasks, then the task set will be schedulable. Now, if we plot this utilization bound, see this is the utilization bound, right. Anything having utilization more than this will not run under EDF, or under RMA. So, if you plot this value with respect to n, you will get a plot like this. When n is equal to 1, see here, n is equal to 1, see the origin here is 1 actually, because 1 is the minimum number of tasks we will consider. So, how much is it coming? When n is 1, what is the maximum utilization? 1. So, 1 into 2 to the power 1 by 1 minus 1. So, this is 1 into 2 minus 1 is equal to 1, right. So, 100% utilization can be achieved when just one task runs. But what about when two tasks run? So, 2 into 2 to the power 1 by 2 minus 1 will be 2 into 1.414 minus 1 is 0.414 into 2 is 0.82. So, for one task it is 100%, for two tasks it will be 81%, 3 tasks will be less, and then it comes here and finally saturates when the number of tasks is large. What about when n is infinity? Okay, so when n is infinity, it will be infinity into 2 to the power 1 by infinity minus 1, and that is a indeterminate form, isn't it? Because 2 to the power 1 by infinity is 1, 2 to the power 0 is 1. So, 1 minus 1 is 0 and infinity into 0 form. So, let us look at that. The maximum utilization for a schedulable task set falls as the number of tasks increases. For one task, we can go up to 100% utilization of the processor and still the deadline will be met. But when we have 2 tasks, we can go up to 81%. For 3 tasks, we can go up to some 78%. 4 tasks, 75%, and so on. But for a very large number of tasks, we have infinity into 2 to the power 1 infinity minus 1, which is the indeterminate form. Now, to find the value of an indeterminate form, you will have to use some L'Hospital's rule and so on from basic mathematics, and you will find that it is log 2 to base e ln 2, which is 0.692. So, if the number of tasks is reasonably large, 10, 20 or something like that, you can think of that if the utilization is less than 0.7 or so, it will run. But if utilization achieved for the processor is more than 70%, the task set will not run, and 70% is not a large value, right? The processor is remaining idle 30% of the time, isn't it? So, this is the bound, the Liu-Leland bound is that as long as the number of task set is large and utilization is less than 70%, it will run. Let us take an example. Check whether the following task set is schedulable using RMA. So, please work it out. The condition for schedulability is simple. If you have forgotten the expression, look at it. N into 2 to the power 1 by n minus 1, as long as that is greater than the utilization achieved, the task set should be schedulable. So, the example, there are 3 tasks. The first task execution time is 1 millisecond and the period is 4 millisecond. Second task execution time 2 millisecond, period 6 millisecond. Third one execution time 3 millisecond, period 20 millisecond. So, first tell what about the priority, which one will have highest priority under RMA? T1 will have the highest priority because its deadline, its period and deadline which are the shortest. The second one is second highest, third one is the third highest. Now, tell me whether this task set will run under EDF. Please work out. So, you will have to first find the utilization and check whether it is less than the utilization bound. So, what is the utilization you are getting? 11 by 53, is it? 15, 11 by 15. Is everybody getting that 11 by 15?
0.73.
So, is 11 by 15 0.73? Yes, it is. So, 11 by 15, and what about the utilization bound? 3 tasks are there. So, n into 2 to the power 1 by n minus 1. Okay, see here there is a solution. See 1 by 4 plus 1 by 3, isn't it? Oh sorry, 2 by 1 by 3. 1 by 4 plus 1 by 3 plus 3 by 20 is 38 by 60. Is that okay? 15 plus 20 is 35 plus 38. No, sorry, 9, 43. Sorry, here there is a mistake here. 44 by 60 it should be. So, this is 15 plus 20, 35 plus 9, 44. I am sorry, I have done a mistake here. Should be 44 by 60. So, that is 11 by 15. Yes, he was correct. Now, the first condition is satisfied, 11 by 15 is less than 1. Now, the second utilization bound we have to check, n into 2 to the power 1 by n minus 1 is, if you simplify this, you will get 0.778, and 0.778 is less than 0.73, isn't it? 11 by 15 is 0.73. So, 0.73, actually there is a mistake, it should have been 11 by 15. So, 0.73 is less than 0.778. So, the task set is schedulable. Now, as we were saying that the utilization bound 69% for large number of tasks is actually does not look a good utilization for a processor. It was proved later in end of 1980s or so, mid of 80s, that Liu and Leyland's condition is actually conservative. If a set of task passes the Liu-Leyland condition, then definitely it will be schedulable. But if it fails it, but still there is chance that it will be schedulable. So, Liu and Leyland is a sufficient condition, but not a necessary condition. Even if it fails Liu-Leyland, still you can try. And the completion time theorem was proposed to check whether a task set is schedulable. Even if it fails the Liu-Leyland condition, you should check for the completion time theorem before saying that whether the task set is schedulable or not. Now, just to take an example, let us look at these 3 tasks. Task T1 20 and 100, task T2 is 40 by 150, and task 3 is 100 millisecond is the runtime requirement, execution time requirement, and 300 millisecond is the period. So, if we try it out, you will say that the utilization of the 3 tasks, the first one is 20 by 100 is 0.2, second one is 40 by 150 is 0.265, and the third one is 100 by 350 is 0.286. If you sum it up, it will be 0.753, and 3 tasks, the Liu-Leyland bound or the utilization bound is 0.779. So, this task set is also schedulable. Does that example look okay? Okay, please try that out again. And yes.
For this Liu-Leyland bound
Yes.
expression,
Yes.
do we have somewhere that how it has been derived?
Yeah. So, the Liu-Leyland's paper that they published gives the exact derivation. They have theoretically shown the result. It is a complex proof actually. If we discuss the proof, it will take several hours here, and since the result is well established and used everywhere, we have not bothered to really prove it here, give his proof here, because it is a well accepted one and the proof is available. Those who really want to go through it, many books actually give that proof, but the book that we are following even skipped this proof, saying that is actually a complex proof and not really central to learning real time task scheduling. But those who are theoretically inclined want to look at the proof, yes, you can look at it in several of the books, and the original paper which is still available on the net. You can just give the Liu-Leyland schedulability paper, you will get the paper on the net available. It is 1971 paper. So, we look at the completion time theorem, which tells us whether a task set will be schedulable even if it fails the Liu-Leyland test. So, today we are running out of time now, we will not discuss that because it will take some time, 15 minutes or so. So, in the next class we will discuss about the completion time theorem, which goes by the name Liu and Lehoczky's theorem. Right, we will stop here.